In 1944, a locomotive rolled out of Baldwin's shops with no pistons, no rods, and almost no sound at the wheels. It left no hammer blow on the rails, and crews would later claim it could touch 100 miles an hour. Within roughly 5 years, it was pulled from service, and no railroad ever built another one. The PRR S2 was arguably the smoothest, most powerful single-steam locomotive America ever built, and it was a failure for one reason that had nothing to do with power. Why reveals how steam actually converts fuel into motion. To understand why the Pennsylvania Railroad built a locomotive without pistons, you have to look at the violent forces occurring beneath a standard steam engine. In a conventional locomotive, massive steel pistons move back and forth inside cylinders, driving heavy steel rods that turn the wheels. Every time a piston reaches the end of its stroke, it must stop completely and reverse direction, hundreds of times every minute. Because of the massive weight of these rods, engineers must add counterweights to the driving wheels to help balance the horizontal movement. However, this counterweight creates an entirely new problem. It balances the horizontal forces, but causes a massive, unbalanced vertical force. Railroaders call this force hammer blow. At high passenger speeds, this heavy pounding behaves like a rhythmic sledgehammer, literally lifting the driving wheels slightly off the rail and slamming them back down with immense force. This destroys the steel rails, damages the wheel bearings, and shatters the stone track bed below. The proposed remedy was simple: eliminate the reciprocating parts entirely. By using a steam turbine, engineers could generate continuous rotary torque. Instead of heavy rods pushing and pulling, steam would blow against thousands of small blades, spinning a shaft smoothly in a single direction with no reciprocating masses. This continuous rotation promised to deliver exceptional power without the mechanical violence of pistons. The Pennsylvania Railroad capitalized on this design, declaring in promotional brochures that their new engine would completely eliminate track-destroying hammer blow. However, this claim was primarily PRR publicity, rather than an independently measured result. But on paper, the direct drive turbine seemed like the ultimate mechanical shortcut to high-speed dominance. The physical forces that hammered the track also took a severe toll on the locomotives themselves. Conventional steam engines required a massive daily upkeep effort to keep running. A standard locomotive was a complex machine containing thousands of moving parts. To translate the back-and-forth motion of the pistons into rotary wheel spin, these engines relied on an intricate web of valves, heavy steel rods, crossheads, pins, and bearings. Every single one of these linkages experienced severe stress with every stroke of the piston, hundreds of times a minute. This constant vibration and physical pounding meant parts wore out quickly, requiring relentless inspection, lubrication, and overhaul. A loose pin or a worn bushing in the valve gear could easily disable a multi-ton locomotive, costing the railroad valuable time and labor in the repair shops. This constant maintenance cycle made the steam turbine's design incredibly attractive to railroad executives. A turbine stripped away the vast majority of these troublesome parts. There were no heavy rods thrashing up and down, no sliding pistons, and no complex valve gears to keep aligned. Instead, high-pressure steam blew against rows of tiny blades mounted on a single, continuously rotating shaft. This elegant setup promised to reduce wearing components to a fraction of what conventional engines required. In theory, a turbine-driven locomotive would spend far less time in the maintenance shops and far more time pulling trains on the main line. It was a promise of mechanical reliability and reduced labor costs that the Pennsylvania Railroad found impossible to ignore. During the 1940s, hauling coal generated a major portion of the Pennsylvania Railroad's freight revenue. This business model faced an existential threat as early diesel-electric locomotives began appearing on rival lines. For the Pennsylvania Railroad, abandoning steam meant abandoning coal, risking the loss of its most valuable shipping customers, the mines along its tracks. To protect this revenue, the railroad needed a modern locomotive that still burned coal, but matched the smooth, vibration-free ride of a diesel. A steam turbine engine promised to resolve this conflict. By using a coal-fired boiler to spin a turbine, the railroad hoped to achieve diesel-like smoothness while continuing to burn the fuel it hauled. This defense of coal revenue, far more than simple engineering curiosity, drove the decision to build the S2. Steam turbines were already a proven, mature technology when the Pennsylvania Railroad began designing the S2. For decades, this technology had served as the quiet, reliable backbone of global industrial power, generating electricity in stationary power plants and driving the world's most powerful naval vessels. In these massive installations, the turbine was supreme. It operated by channeling high-pressure steam through rows of tightly packed blades, converting thermal energy directly into continuous rotary motion without the violent vibration or high-maintenance wear of reciprocating pistons. When the railroad partnered with Baldwin and Westinghouse, they did not build a turbine from scratch. Instead, the S2's power plant was adapted directly from United States Navy battleship turbine technology. On the open ocean, these marine turbines operated at high speeds for days or weeks at a time, running at a near constant optimal velocity, where they achieved remarkable thermal efficiency and reliable power output under heavy loads. The engineering goal for the S2 was to transfer this high-speed marine efficiency directly to the rails. If a turbine could propel a massive warship smoothly across the sea, it seemed entirely logical that a scaled-down version could haul a heavy passenger train across the flat, high-speed corridors of the Midwest. In theory, once the locomotive reached its cruising speed, the turbine would run in its ideal operating zone, offering a level of fuel economy and smooth performance that no conventional piston-driven engine could match. It was a conceptual leap based on proven maritime physics, attempting to turn the new locomotive into a land-bound warship that could glide effortlessly across the Pennsylvania Railroad's main line. In September 1944, with the United States locked in the final, exhausting year of World War II, a joint publicity announcement from the Baldwin Locomotive Works and the Pennsylvania Railroad introduced a radical new machine. This was not a mass production design, but a single, highly experimental prototype designated as road number 6200. The creation of the 6200 was a monumental collaboration between two industrial titans, divided by their specialized expertise. Baldwin's EE division took responsibility for the massive chassis, the heavy frames, and the running gear. Westinghouse Electric and Manufacturing Company supplied the heart of the project, the complex steam turbine power plant and its double reduction gearing. Historically, the internal Pennsylvania Railroad records do not identify the specific mechanical engineers who directly supervised this project from the railroad side. However, steam locomotive historians emphasize that the railroad possessed a deep-seated corporate culture of bold, sometimes reckless experimentation. The Pennsy frequently designed and built massive one-off prototypes in an aggressive bid to leapfrog its competitors. When the completed locomotive was delivered in the fall of 1944, it was instantly a mechanical celebrity. The September brochure promised a revolution in rail travel, describing a massive locomotive that would glide down the tracks with unprecedented smoothness. Yet behind the optimistic press releases, road number 6200 remained an unproven concept delivered into a grueling transport network, where every engine was expected to run constantly under heavy loads. The S2 was about to move from a clean engineering drawing to the harsh, unpredictable reality of daily mainline operations. When the completed locomotive rolled out of the Baldwin shops, its sheer physical footprint demanded a wheel layout never before seen in railroading history. To carry its immense frame, engineers designed the engine with a 6/8 wheel arrangement under the White classification system. For anyone unfamiliar with how steam locomotives are classified, these numbers represent the physical sequence of wheels from front to back, showing how the engine contacts the rails. The first digit represents 6 small leading wheels, divided across 3 separate axles at the front of the locomotive, which helped guide the massive machine into curves. Next came the 8 large driving wheels on 4 axles, which delivered the rotating power of the steam turbine directly to the steel rails. To complete the layout, the rear of the engine was supported by another 6 small trailing wheels on 3 axles, positioned beneath the massive cabin and firebox to carry its heavy load. This specific configuration, 6 leading wheels, 8 drivers, and 6 trailing wheels, had never been used on any locomotive before, and it would never be used again. Locomotive 6-200 remains the only 6-8-6 steam locomotive ever built. This arrangement was not a stylistic choice or a bid to set records. It was a direct, practical engineering response to the challenge of supporting and balancing an incredibly heavy machine. A turbine and its massive reduction gearbox concentrate an enormous amount of weight in a small area. Spreading this weight across 20 structural wheels was the only way to keep individual axle loads within safe limits, preventing the locomotive from damaging the tracks and bridges of the Pennsylvania Railroad. The design choices behind this massive wheel layout lead directly to the severe material shortages of World War II. When Baldwin and Westinghouse engineers first drafted the S2, they planned for a lighter, more conventional 484 locomotive. However, wartime military priorities diverted high-strength, lightweight steel alloys to warships and combat aircraft, leaving the builders with no choice but to use heavier, standard steel castings for the locomotive's massive frame and turbine housing. This material substitution dramatically increased the engine's physical mass. With its 16-wheel tender coupled, the total weight of the machine climbed to over 500 tons, or more than 1 million pounds. To keep individual axle loads from exceeding the Pennsylvania Railroad's strict track limits, engineers had to distribute this enormous weight. They expanded the wheelbase by adding a third axle to both the front and rear trucks, turning a standard design into the heavy 686 layout. This massive length and weight created immediate, unexpected physical problems. Because of the locomotive's gargantuan frame, exhaust steam clung to the boiler, drifting down and completely blocking the engineer's view of the track at lower speeds. Early photographs of the S2 show it running with small, unobtrusive smoke deflectors near the front. These proved entirely inadequate for the visibility issues on the line. To keep the crew from running blind, the railroad replaced them with massive, steel elephant ear smoke deflectors, mimicking the design used on the experimental S1 duplex. These tall plates caught the wind as the train moved, lifting the heavy coal smoke up and away from the cab windows. Behind the steel smoke deflectors sat the source of the locomotive's raw energy, a giant coal-fired boiler. This conventional Bell-pair boiler was designed to generate steam at a working pressure of 310 pounds per square inch during normal, high-speed operation. While the boiler itself followed traditional railroad design principles, the steam circuit it fed departed completely from the standard mechanics of the era. In a typical steam locomotive, high-pressure steam enters the cylinders, pushes the pistons, and blasts out through the exhaust nozzle in rhythmic, explosive cycles, creating the familiar chugging sound. The S2, however, routed its steam through a continuous path. High-pressure steam surged from the boiler dome directly into the turbine housing, where it expanded through the closely spaced blades to rotate the drive shaft. Because the S2 was a non-condensing locomotive, it carried no heavy condensing apparatus to cool the spent steam back into liquid water. Instead, the exhausted steam was vented directly into the atmosphere through the smoke box. This non-condensing exhaust path gave the S2 a distinct acoustic identity. Instead of the sharp, rhythmic exhaust pulses of a piston engine, the locomotive emitted a continuous, steady roar. Observers standing along the right-of-way reported that the engine did not sound like a traditional steam train. Instead, as the 6,200 sped down the line, it produced a characteristic, powerful whoosh, a sound that onlookers compared to a massive blowtorch or a steam line venting at a power plant. This constant rushing sound reflected the continuous, unbroken flow of steam through the circuit, completing the physical picture of the power plant before that steam ever met the gears of the drivetrain. The S2's mechanical layout was defined by an incredibly bold yet unyielding engineering choice. The massive forward turbine did not transmit its power through a variable gearbox, a clutch, or an electric generator. Instead, Baldwin and Westinghouse designers directly coupled the high-speed turbine shaft to the locomotive's driving axles through a single, fixed ratio gear set. In this direct drive setup, a double reduction gear train translated the high-speed rotation of the turbine down to the wheels. This massive gear assembly sat directly on the locomotive's frame, with a central bull gear driving the second and third axles, while traditional side rods linked the remaining wheels to distribute the power. To picture how this worked on the rails, imagine taking a high-performance, high RPM racing engine, putting it into a car, and welding the engine's output shaft directly to the rear axle. There is no clutch to let you slip into gear, and no transmission to shift from first to fifth. If the car is stationary, the engine is completely stopped. If the car moves at 5 miles per hour, the engine turns at a slow crawl. Only when the vehicle reaches its top speed does the engine spin at its designed efficient RPM. This was the exact mechanical reality of the S2. The rotation of the turbine blades was locked to the rotation of the driving wheels, and therefore, directly to the road speed of the train. For the turbine to spin at its optimal high-speed range, the entire 500-ton locomotive had to be screaming down the main line. This direct drive setup eliminated the heavy electrical components of a diesel-electric locomotive, as well as the complicated multi-speed gearboxes found in other experimental machines. The designers believed that by skipping these intermediary systems, they could avoid the friction and energy losses that occur when transferring power from an engine to the rails. They created a drivetrain of remarkable simplicity, where the immense rotary power of expanding steam was transferred almost instantly to the steel rails. But this simplicity came with an unforgiving physical trade-off. Because the turbine could not be disconnected or geared down to match different speeds, the locomotive had to rely entirely on the flow of steam to regulate its speed and power from a dead stop. This locked relationship between turbine RPM and track speed meant the S2 was physically incapable of adjusting its mechanical advantage, setting up a direct conflict between the inherent nature of steam turbines and the basic operational demands of a working railroad. A steam turbine is fundamentally an aerodynamic machine. Unlike a conventional piston engine, which uses static pressure to push a metal piston back and forth, a turbine relies on the velocity of steam rushing past thousands of tiny curved blades. To extract this energy efficiently, those blades must spin at a high, precise velocity that matches the speed of the incoming steam. When the S2's turbine spun at its design limit of 9,000 RPM, the steam pushed smoothly against the blades, transferring nearly all of its kinetic energy into rotary motion. But because the S2 had a fixed ratio drivetrain, the turbine's speed was locked to the road speed of the locomotive. This rigid relationship meant the turbine could only spin fast if the train itself was flying down the track. When the locomotive slowed down, the turbine was forced to slow down with it, creating a highly unforgiving efficiency curve. When the S2 was starting from a dead stop or crawling at low speeds, the turbine blades were turning slowly, if at all. Yet to get a massive 500-ton train moving, the engineer had to open the throttle wide. High-pressure steam rushed into the turbine, but because the blades were nearly stationary, the steam could not transfer its kinetic energy. It simply blew straight through the open spaces between the slow-moving blades and escaped out the exhaust steek, leaving the locomotive with very little actual tractive power for the massive amount of steam it consumed. This aerodynamic mismatch created a distinct operational threshold. While historical sources vary on the exact cutoff, they generally identify a critical transition zone between 30 and 40 miles per hour. Above this speed, the turbine functioned with excellent efficiency, consuming far less steam than a conventional piston-driven locomotive. Below 30 miles per hour, however, the turbine became a massive steam vacuum. To maintain any pulling force at these low speeds, the turbine had to gulp unprecedented amounts of steam. This massive, sudden demand quickly overwhelmed the boiler's capacity. Steam left the boiler much faster than the coal fire could heat and vaporize new water, causing the overall boiler pressure to collapse from its normal working limit of 310 pounds per square inch to as low as 85 pounds. To fight this pressure drop, the firemen had to shovel coal and pump water at unsustainable rates. Instead of producing useful work, the S2 was effectively burning through its coal and water supply and venting the wasted energy directly into the atmosphere. A Class 1 railroad is not a laboratory. It is a relentless, daily obstacle course of starting, stopping, climbing grades, and negotiating speed-restricted curves. When the S2 coupled to a heavy passenger train at a station, the crew faced the most fundamental task of railroading: getting a stopped train to move. Traditional reciprocating locomotives leverage maximum steam pressure inside the cylinders at 0 miles per hour, producing high starting torque. The S2, however, had to dump massive volumes of steam into a stalled turbine just to coax the wheels into motion, wasting energy before the wheels even turned. Climbing an incline, slowing down for a yellow signal, or rounding a curve presented the same mechanical crisis. Each time track conditions forced the speed down, the turbine's RPM dropped with it, dragging the engine back into its highly inefficient operating zone. To accelerate back to cruising speed, the firemen had to struggle to maintain steam pressure, forcing the boiler to its absolute limits. This operational loop exposed the defining paradox of the S2. The locomotive did not suffer from a lack of raw horsepower. Once flying down the flat stretches of the main line, it could easily match or exceed the performance of contemporary piston-driven engines. But a working railroad cannot operate solely at high speeds. The true measure of a locomotive's utility is not its maximum power once moving, but its ability to deliver reliable, useful power at 0 miles per hour. Without a transmission or variable gearbox to decouple turbine speed from road speed, the S2 remained a magnificent high-speed machine physically incompatible with the stop-and-go reality of everyday rail service. In late 1944, the Pennsylvania Railroad moved Locomotive 6200 out of the laboratory and onto the high-speed racetracks of the Fort Wayne Division for its first revenue service. Assigned to the 283-mile corridor between Chicago, Illinois, and Crestline, Ohio, the massive prototype began handling scheduled passenger trains, including flagship runs like the Broadway Limited and the Trailblazer. This flat, straight territory was interspersed with localized speed restrictions and grades up to 1.2%, a real-world proving ground that demanded both rapid acceleration and sustained high-speed running. On March 30th, 1945, the railroad coupled a heavily instrumented dynamometer car behind the S2 to record its performance under precise scientific conditions. The locomotive was assigned to haul a massive 17-car passenger consist. Once the train cleared the terminal limits and entered the open stretches of the main line, the engineer opened the throttle wide, letting the turbine build momentum. With the turbine blades spinning near their optimal aerodynamic efficiency, the S2 unleashed its massive shaft horsepower. The dynamometer records documented the locomotive holding a steady speed of 110 miles per hour for a continuous 30-mile stretch of track. British locomotive engineer E.S. Cox, observing the run, noted that the machine sustained speeds above 100 miles per hour for 12 consecutive minutes. The ride inside the cab was remarkably smooth, free of the violent vertical dynamic forces that typically plagued reciprocating steam engines pushing past 90 miles per hour. This run confirmed that when freed from low-speed constraints and allowed to run at its design velocity, the direct drive turbine delivered on its high-speed promises, moving the heavy passenger cars with a smooth gliding motion that rivaled any conventional passenger locomotive on the rails. At these speeds, the S2 transformed from an operational headache into a mechanical revelation. Crews who rode in the cab of number 6200 reported an experience that felt completely alien to anyone accustomed to traditional steam, because the turbine eliminated the heavy back-and-forth thrashing of pistons and rods. The violent, rhythmic shaking that characterized standard locomotives simply vanished. There was no piston-driven pounding, no vertical shuddering, and none of the brutal cab vibrations that typically exhausted crews on long, high-speed runs. Instead, the S2 glided over the rails with an unprecedented, liquid-smooth delivery of power. At the wheels, the mechanical action was nearly silent. Observers on the ground heard only the rush of wind, the continuous roar of the exhaust stack, and the clicking of the wheels over rail joints, entirely free of the clanking and clanging of reciprocating rods. This lack of vibration was more than just a matter of crew comfort. It represented an almost total elimination of the destructive hammer blow that shattered track beds and wore down bearings on traditional lines. Once the turbine reached its optimal high-speed range, this smoothness translated directly into massive, effortless tractive effort. Free from the friction of sliding valves and heavy reciprocating parts, the locomotive could sustain an immense, uninterrupted power output of over 6,000 drawbar horsepower above 40 miles per hour. Under these ideal conditions, the direct drive design achieved its original purpose, delivering a steady, unrelenting surge of momentum that conventional locomotives could match only through immense mechanical strain. It was a fleeting glimpse of what steam turbine technology could achieve when allowed to run exactly as designed. The celebrated rating of 6,900 horsepower requires careful definition to prevent it from becoming a false certainty. This figure represents the design rating of the forward turbine shaft at 9,000 revolutions per minute, reflecting a claimed 97% mechanical efficiency through the gearbox. This shaft output is fundamentally different from the cylinder equivalent horsepower used to measure conventional reciprocating steam engines. In a similar way, the legendary reports of the locomotive running at speeds well over 100 miles per hour must be treated with caution. Outside of the single instrumented test run, these claims of extreme speed rely almost entirely on crew testimonies and later railfan recollections. While these anecdotes successfully capture the smooth sensation of riding in the cab, they are not verified by primary source data. Without official records, these stories remain valuable pieces of railroad lore rather than scientific proof of the engine's everyday capabilities. The S2's struggles became even more pronounced when it had to run backward. While the forward turbine was built for high-speed runs, the reverse turbine was an afterthought. It could only propel the engine up to 22 miles per hour. Because historical records do not explicitly quantify its maximum output, engineers estimate its reverse capability at approximately 2,500 horsepower. Crews describe the reverse gear as weak and highly uneconomical, making basic yard switching and terminal backing maneuvers a difficult, fuel-intensive chore. This mechanical imbalance rippled across daily operations, highlighting the severe route limitations of the prototype. The locomotive's massive consumption of coal and water at lower speeds restricted its overall range. This poor water economy meant the engine could only run on specific lines equipped with frequent water-filling stations, stripping the railroad of the flexibility it needed to assign locomotives where they were most needed. It was bound to the flat Chicago to Crestline corridor, unable to venture onto secondary routes. Keeping the single engine in service created a massive, specialized maintenance burden. Because the S2 was a one-off experiment, the railroad's maintenance shops held no inventory of spare turbine blades, gears, or heavy bearings. Every breakdown meant long delays while technicians custom-fabricated replacement components. Operating a one-unit experimental program carried a high economic cost. Without a production fleet to spread these expenses across, the S2 became a financial drain on the company. The railroad had to maintain specialized tools and train technicians to service a solitary locomotive, a burden that conventional steam and mass-produced diesels simply did not require. Every hour spent idling in the shop represented lost revenue. The ultimate challenge to the steam turbine did not come from conventional steam engines, but from a completely different propulsion design. During the late 1940s, electromotive division diesel-electric units began appearing on competing lines, presenting a direct alternative to the S2. Unlike the direct drive turbine, which locked the power plant's speed to the rails, a diesel-electric locomotive used an electrical transmission. The onboard diesel engine turned a generator, which produced electricity to power traction motors mounted directly on the axles. This system functioned as an infinitely variable transmission. The diesel engine could run at its most efficient speed to generate maximum electrical power even when the locomotive was at a complete stop. As a result, these new units delivered massive starting torque and superior low-speed tractive effort precisely when a train needed to start, climb steep inclines, or negotiate tight curves. This electrical transmission made usable tractive effort available across the entire speed range, eliminating the dead zones that crippled the S2. This new power plant also significantly reduced the workload of railroad crews. Firemen no longer had to shovel tons of coal or constantly manage water levels in a volatile boiler to prevent pressure collapses. A single engineer could control multiple coupled diesel units from a cab using simple, standardized controls. The logistics of running a railroad changed completely. Diesels did not require frequent stops at water towers, nor did they demand custom-machined replacement parts for a solitary prototype. The diesel-electric was a direct answer to the S2's primary operating weakness, offering unmatched flexibility and efficiency from 0 miles per hour to 90. In the summer of 1948, the Pennsylvania Railroad exhibited the S2 on a national stage at the Chicago Railroad Fair. The massive locomotive became a centerpiece in the grand outdoor pageant, wheels a-rolling, standing as a symbol of coal-fired steam power alongside the experimental T1 duplex. Yet this public celebration soon gave way to mechanical reality. In August 1949, while back in regular service, the locomotive suffered a severe turbine failure. The high-speed rotor, designed to spin at 9,000 RPM, experienced an internal bearing break that caused extensive damage inside the casing. Faced with the high cost of custom fabricating replacement parts for a one-of-a-kind prototype, the railroad decided against repairs. That same month, the S2 was withdrawn from active revenue service, bringing its brief 5-year operational career to an end. Following its sudden withdrawal in August 1949, the disabled locomotive was moved to Crestline, Ohio, and later to the Altoona test plant, where it remained stored pending final disposition. For nearly 3 years, the silent 500-ton prototype sat in the yards as the railroad's rapid transition to diesel-electric power made any prospect of rebuild obsolete. Having entered service in late 1944 and ceased operations in 1949, the S2 had completed an active service career of just under 5 years. On January 1, 1952, the Pennsylvania Railroad formally retired number 6200 from its active roster. Later that year, the physical destruction of the experimental machine began. Workers at the railroad's Altoona shops completed the formal scrapping of the locomotive in 1952, cutting the massive frame, boiler, and direct drive turbine housing into scrap metal for reclamation. Reconstruction of the S2's final chapter rests on a fragmented historical record, as no official Pennsylvania Railroad disposition files for road number 6200 survive in the public domain. Instead, the chronology of its operations and ultimate demise must be verified through secondary documentation and corporate archives. Primary evidence remains scattered across mechanical department files, Baldwin Builder records, and Westinghouse technical drawings preserved at the Hagley Museum and Library, the Pennsylvania State Archives, and railroad historical societies. Original blueprints from these repositories authenticate the physical arrangement of the direct drive gearing and the axle spacing of the 686 frame. These primary sources help separate design specifications from real-world performance, showing that the famous 6,900 horsepower rating was a calculated shaft limit rather than a measured drawbar output, establishing a clear line between engineering ambition and physical reality. The S2's legacy isn't that it lacked power, but that it couldn't deliver it where railroads actually operate, at 0 miles per hour. It remains a monument to a correct idea bound to the wrong drivetrain. Today, as engineering still balances peak performance against real-world usability, the fate of number 6,200 reminds us that raw power is useless without the flexibility to start. What do you think of this turbine's design? Let me know below.